Let's talk about the Earth's energy budget. The vertical displacement of energy in the climate system is studied from satellite measurements. There is some uncertainty, and data from different studies may differ somewhat. Here we follow the NASA data. Solar energy accounts for 99.9% of the energy received by the climate system, so the climate changing capacity of other energy sources is very small. An average of 340 watts per square meter reaches the Earth in the form of shortwave radiation, which is 100% of the energy received. 29% of this energy is reflected by the atmosphere, clouds, and surface without adding energy to the climate system. This is called albedo. 1.2% is absorbed in the stratosphere, mostly by ozone, and 22% is absorbed in the troposphere, mostly by water vapor and liquid water in clouds, so the atmosphere absorbs 23%. The remaining 48% reaches the surface and is absorbed. Since the oceans cover 71% of the surface and have a lower albedo, meaning they reflect less light, most of this energy ends up in the oceans. If the planet does not emit as much energy as it receives, its temperature will change until it does. There is a lot of talk about the greenhouse effect causing the atmosphere to warm the surface. This is not true. The atmosphere is cooler than the surface, and it is the surface that warms the atmosphere. What happens is that the greenhouse gases make the atmosphere very opaque to the long-wave radiation emitted by the Earth, and almost everything that is emitted from the surface is reflected back to the surface by the atmosphere. There are two exceptions. 12% of the energy is emitted through the radiative window of the atmosphere, a part of the spectrum that greenhouse gases do not absorb. And the net emission of energy between the Earth and the atmosphere is positive, so another 5% of the energy received from the Sun passes through the atmosphere as IR radiation. What happens to the rest of the energy that needs to be returned? How does it get to the emission level? Another 5% is by convection, as hot air rises, but most of it is in the form of latent heat. Evaporating water requires an enormous amount of latent heat, which is released in the upper troposphere as the water vapor condenses. From there, all the rest of the energy is emitted into space as IR radiation. Clearly, to maintain its temperature, the Earth must return to space all the energy it receives from the Sun. When scientists encounter these kinds of equilibrium conditions, what they do is assume that the equilibrium is real, and this allows them to give a mathematical solution to a process that they otherwise could not. This also happens in chemistry when you assume equilibrium conditions in reactions. It is useful for studying the process, but one should not lose sight of the fact that equilibrium is not real. Climate scientists have developed the following equation to describe the hypothetical energy balance of the Earth. You can find this equation written in several different ways. One of them is the one I show here. The left side of the equation is the energy entering the system. It is the energy from the Sun that reaches the Earth, minus the energy that bounces back due to albedo. The right side is the energy leaving the Earth, which is proportional to the efficiency of emitting infrared energy, or emissivity, times the Stefan Boltzmann constant and the Earth's emission temperature to the fourth power, which is the average temperature of the Earth's average emission height, which is about 6 km high. But scientists prefer to use the temperature of a black body that emits with the same spectrum as the Earth because it is a fixed value, even though the Earth is not a black body and there is a small error. If this equation were true, the temperature of the Earth would always be proportional to the energy received from the Sun, but we know this is not the case. It varies from day to day, and over the course of a year, it varies by an astonishing 3.8 degrees Celsius. This figure shows 26,000 temperature measurements over 5 years from space. Over that period, it varies by as much as 8 degrees Celsius. This is much more variable than the energy coming from the Sun, which is essentially the same on the same day of the year. Two things are important about this graph. The first is that the temperature of the Earth is not the 255 Kelvin for a black body that scientists use, but 251 Kelvin, or minus 22 degrees Celsius, or minus 8 degrees Fahrenheit. The second is that the Earth is actually colder when it is closer to the Sun and receives more energy, during the Northern Hemisphere winter, and warmer when it is farther from the Sun and receives less energy. The Earth's energy balance equation is useful, but it is not real because it assumes things that are not true and does not describe the real energy behavior of the Earth. One problem with science is that assumptions are not tested, so you have to be very careful with them. The scientists who developed the equation knew that it was an ideal case that does not hold true, but the scientists who come after and learn it in graduate school do not know that it is an assumption and firmly believe that it reflects physical reality when it does not. They will not be told in any climate book or article that the equation is not real. That's why it's so important to know about climate science, because what you find out is that we don't really know what's happening to the climate or what's causing it. And that's a very weak basis on which to make costly policies. Thanks for your attention. If you like climate science and want to know more about it, you can buy my books, which are available at Amazon and other internet stores. You can also subscribe to my YouTube channel.